So today I want to share also it's a very new topic to me. It's called the scaling laws of I would say neural networks because I don't think it only applies to LLM, but it's very useful to use the scaling laws to predict how LLM, what's the performance of LLM when you scale up the data sets, the computing resources, or scaling up the parameters, the model parameters. And the whole slides, I actually take most of it from the Stanford LM course, the CS324. So I think it's a very good connection of all the relevant simple laws detected to predict the LM performance. So what motivates the problem, right? So we all know that neural network requires hyperparameter tuning. Well, but the hyperparameter tuning comes at a cost, right? So not just it's expensive to tune these models like on a distributed server on the cloud, right? So it will actually cost you dollars to do that, but also like in terms of environmental considerations, like it will actually also have emitted lots of like carbon dioxide, like because it requires lots of computing resources to do that. So how about like if we can identify a simple rules to predict how the model performance will be according to the hyperparameter configuration without actually implement that configuration and run through the whole data sets and get the performance. That will save us a huge cost. So how do we solve this? Well, first, yes, we can guess and pray. Just hope that it can work. And the second is like we can do an exhaustive search. Basically, we just try all the configurations. But as I said, right, it's very expensive to tune the network to identify the optimal configurations parameters, and also it's not very environmental friendly. The third option is how about like let's see whether there's any simple rules. It's kind of like a simple prediction, like maybe just a linear prediction, right? That can help us forecast the performance, the model performance given the hyperparameters. And also it will give us suggestions of how we should configure the model without actually running the full hyperparameter tunings on that model. Uh, actually this section is on using simple predictive laws to predict the behaviors of language models. So in this session, most of the use cases and neural network is mainly, or LLM is on the language models, NLP task. And you will see today that, and also in the literature, that the scaling laws like very simple kind of a linear fitting lines can help predict the model performance given the configurations. So the other way is like you need to tune the hyperparameters on big models, right? And it can be quite costly. And the new and more exciting ways is that if we have a forecasting, a prediction of the model performance, we can actually just fit that model. We just like generate the performance with a smaller model first, and then we can fit these data points with these simple like scaling laws models, and then we can use that fitted simple model to predict what's the performance when you scale to a larger model. Basically, you do a extrapolate to estimate the performance for the larger models. So here is some example, right? For example, you want to estimate what is the model performance, so either validation loss or test loss, you want to estimate versus the computing resource, right? So usually like the more resource, more computing resource, which means that you can run larger model, you can run a larger data sets, or you can even train like a one model on, but further like to more running the model, train it on more steps, right? And then you will see like how the loss is going to kind of aligns with this lower bound of test of the loss versus the computing resources. I will dive deep into this chart later, but actually this is the line that we want to get, right? So basically, if we know what is the computing resources we have, we kind of know what is the best model performance we can get given the computing resources. We can also use in the same to identify what is the right configuration, say the number of layers in a neural network, right? And you can actually plot, you can use like one layer, and you can still have an increasing parameters. Basically, you can just increase the hidden dimensions, right? And you can still have like a larger and larger model, and then you can see what is the test loss for each of the model performance. And then when you increase the layers from 1 to 2, you will see another curve. But as you see, like people find that when you grow deeper and deeper, sometimes there's a region that having a more deeper layers actually won't help with the performance much until the model parameters, when it reaches certain threshold, when the model has lots of parameters, and then the difference of adding additional layers becoming more obvious advantage for the test loss. So I will dive deeper into what this chart means later, but overall, this is what we hope to get, right? So we want to see what is a relationship, for example, between the loss and the computing, or the data size, or the model size, for example. And also we want to understand how different model configurations is going to help going to predict the test loss. So what is the best model configurations? Yeah, so we want to study the test loss against the compute. We want to study the test loss against the data size, basically the number of tokens in your training set, and also the test loss against the parameters. Intuitively, it's all monotonic, right? So we know that if we have more compute, more data size, more parameters, the test loss will decrease, right? And more interestingly, people identify that actually it's a log linear relationship. So if you take a log of the test loss, and also you take a log of the compute, or take a log of data size or parameters, you will identify a close to linear relationship between these two. So yeah, that's actually the main conclusion if you want to identify the relationship. And also people find that it can even hold in non-standard setting, which means that you train a model, say you train a model on internet books, Wikipedia, or Common Core dataset, and then your test set can be another different dataset, say a web text. So basically your trained dataset hasn't seen the test set before, and it still follow the same kind of the same linear line of the test loss of the new unseen test set over there. So it's pretty magic to me, and it seems that they all follow a similar ratio, but the intercept kind of different. So we in this talk, so we will first see how the performance is going to change versus the data size. Are there any simple rules that can determine how data affects the performance? And also the hyperparameters. Is there any optimal hyperparameters the same across different data or models, so that we can directly start with this optimal kind of suggested hyperparameters right from the beginning? And And the third is, does the benchmark performance follow the predictable trend? It's basically say if we are able to fit this scaling laws to small models, and if we scale it up to large models, does the predicted performance aligns with the actual performance of the larger models? So this is what it's trying to answer. So data versus performance. And actually there's like a simple formula that can map data size to the error. And actually if you zoom out to a big, like the full spectrum of data size, you can break it up into 3 sections. So the first is or regions. So the first is the small data region, which means that your data connected maybe not general enough or maybe best. So your performance can be bad, right? So your generalization error can be high in the beginning when your data is small. And then as you connect more and more data and your model see more and more patterns, there will be a kind of a log linear decrease of the performance versus the data size. Okay. So in the end, so if you continuously like connect more and more data, it kind of saturates, and then it will kind of converge to the irreducible error. This error may due to just the noise in the data, or maybe just due to the patterns, the complicated patterns, in the data. In the reality, right? So the performance usually is lie between in the power law region, while you will observe a log linear relationship over. So it's usually very hard to get to the irreducible error region unless your problem is very simple, and then a few data points will already saturate the performance. So we will mainly focus on the power law region. So empirical observation is, so this is your data size and this is your test loss. So we can fit, if we take a log of the data size and take a log of the test loss, you can fit almost like a very simple linear curve around. So you can see that so this is like a power, right? So if you take a log, it will becomes a linear relationship. And people identify this scale-free or power law relationship. So and then people may ask, like, why is a log linear relationship? So before like diving deeply into why, people actually observe this phenomena across different tasks, right? Such as like machine translation. When they increase the training data size, they see a linear of the log relationship. Also for the speech and the language modeling, the same linear relationship occurs in the log scale. So people have been detecting this for quite a while. So why do scaling laws shows up? We all know that the error should be monotone, right? So it will be like linearly decaying. But why is it linear in the log? Right? So actually the conclusion is like estimation error naturally decays polynomially. But we can walk through a simple example just to see like why the scaling laws stands. We can take a very simple example as, say, if we want just to estimate the mean estimation, right? Say if we have the x to the normal distribution, and then we take the average, just as a simple mean. And then what is the error based on this estimation? So basically, just you can calculate the expected mean error, which is based on the covariance divided by the variance divided by n, right? So you normalize by the number of samples in your set. And if you take a log, so it's a linear relationship, right? So if you compare the log of the error versus the log of the data size, which is n, it's a linear relationship. So basically from these like intuitive examples, we can see that it kind of like follows like a very straightforward linear relationship between the log. But actually, people find that for the classical models, such as the regression, it do have the 1/n scaling. So it means that it has like just this relationship. So this is the log of the data size, and this is the log of the loss. And they just follow like a very simple relationship, just as what we derive for the mean estimation. But when people actually fit this line to various NLP tasks like machine translation, speech, or the others, they find that it's not as simple as this relationship. So then people wonder, okay, why is this different from prediction? Why is not this simple? So what factors affect the ratio of the line? Right. So right now we know it's a line, a simple line, but what is a factor for that the ratio of the line? The scaling laws, we know that the scaling laws, so basically different problem, different data sets may have a different ratio. So that ratio is alpha. And people have shown like, well, I would not say it's like theoretically, maybe people have proved it theoretically, but people also show it like empirically through experiments that the slope alpha is connected to the intrinsic dimensionality of the data. So say if the data is like 2 dimensions, 3 dimensions, or even higher dimensions, then it's then that slope will be reflecting the intrinsic dimensions of the data. I think it's a very interesting discovery, although I'm not sure right now whether it's theoretically proved on that. And also people say, okay, then how does the data size, so we know that how does the data size relate to the performance, but then how does the data composition affect the performance? Right, and then people, okay, doing the studies, and then you can combine the data sets at a different distribution, different ratios, and then it finds that it will affect the offset, right? So the y, you see the offset will be different on y's. The slope actually stays the same. So it's a very interesting discovery, means that the data for that specific problem, the intrinsic dimension of the problem and of the data is stays the same. But this intercept or the offset still matters, right? Because it tells you, because it will affect the end performance. We want the offset to be as lower as possible. And then people say, okay, how can we lower the intercept or the offset? And then they do some experiments, such as say we have only 2 data sets, right? And then so Q is like, say, how much we will utilize the second data sets on the same problem. So when you just use one single data set, the intercept is pretty high. And as you add in the training set, as you adding in the second data set, you see the test loss or the intercept kind of drop. And actually people identify what is the optimal kind of combination of the training set so that the intercept is the lowest. The lowest means that you can have the lowest test loss. Comparing to your for that data configuration, and people find that is actually around 0.5, which I think it's to our intuition, right? Because we always want to connect the diverse data set as possible to train the model so that we have the best test loss of that diversified data set. It's interesting to see that how they kind of relate the intuitive discovery to the scaling laws of predicting the performance. So we see that there's a linear relationship between the log, between the data size and the error in the log scale. And it actually holds across different domains and models. And it depends on the data sets and the problem. You may observe a different, like a different ratio or different intercept for the linear model. And also, like the theory understanding that is similar to the generalization bound. Like, for example, the mean estimation example, we can see that how it kind of convert the error to a linear relationship. And also the application can be that it proves that we need to connect as diversified as data, training data as possible, so that we can move that line, that linear line down. So we can reduce the intercept, so that we also reduce errors on that scale. Now let's move on from the data scaling to the model scaling. So basically it's like how can we efficiently design the huge language models? We have so many different choices, right? So we can choose different architectures. We can choose different optimizers. Also, we can choose like different, say, number of depth layers, etc. So there are so many choices. So how to best allocate our limited resources, right? Should we train the models longer, or should we just put out a bigger model whenever possible? Should we connect more data and get more GPUs? So the scaling laws provides a simple procedures to answer these questions. So here's some examples. Like in terms of the architecture choices, like one straightforward can be transformers always better than LSTMs. One way could be that you can just train a transformer LSTM, and also you can train like a really large LSTM or transformers and then compare the performance of that, which can be quite expensive. The scaling laws ways is you just train smaller models. So you just train a small models of LSTM and small models of transformers, and then you observe what's their test loss. And then you again will detect a linear relationship. So it's kind of a linear relationship. And then you can scale it up to predict what's the performance would be like if we increase the model size. And from here we see that the gap is obvious, so people kind of converge to use all the transformers for the NLP task instead of the LSTM. Yeah, so without actually training like millions or even billions parameters to compare really big LSTM or transformers, you can just train the smaller ones, comparing the performance, observing different data points, and then try to scale it up to a larger scale. The same to the optimizer, right? So people can also study the different optimizers with small models first, right? So they can use a smaller data set, smaller models. And then the orange one is using the ADAM optimizer, and the blue one is using the SGD. So this is this kind of the line is what is observed when you train smaller models, and then you can extrapolate to larger scale, like to predict what it would be like when we scale it up to larger scale. So from this chart, it seems that ADAM seems to perform better, at least for this task, when they train the small models for what task, what's their task at hand. So the ADAM seems to be consistently performing in the lower, like a smaller data scale and model scale, and thus they also predict, since it follows the linear relationship in the log scale, thus they also conclude that the performance, the gap should also persist in the larger scale. Another interesting question is like the number of layers. So does the depth or the weight makes a huge difference of the language models? So there is a huge difference of, so this is the one layer configuration. And then this is a 2-layer configuration, and also 3-layer. And also you can always increase the width of the network so that the parameters will grow, right? So you can still get a larger model, but basically the decision is, should we make it wider or should we make it deeper? From here, we see that there exists a big difference between 1 layer and 2 layers. But from 2 layers to 3 layers to 6 or more than 6, the gap is small, right? Comparing to the jump from 1 to 2. So like more layers actually will see like below when the model size is small, like below 10 to the power of 7, it's pretty close. But as you kind of further increase the model parameters to 10 to the 9th or even more, such as the LLM that we have right now, the performance gain will be larger, comparatively larger. Still tiny, but I mean, if you really scale it up to a really large scale model size, the gap will enlarge. So basically, people conclude that for the depth configuration, there's a region in the model size. They call it a depth inefficiency. So for the smaller model size, increasing the depth actually does not help much. But instead, if you like have a larger and larger model, adding additional layers will help the test loss. Yeah. So that means that it's actually not kind of it's not like a straight linear line, right? It will actually be region dependent, based on along the model size. So there will be like a different regions. Well, within the smaller region, the depth does not improve much, but in the as the model size grows larger and larger, the depth can play a more important role to improve the model performance. When people observe this, they also it's a very interesting paper of Jurassic 1 model. So basically, they take the GPT-3 model. So this is the corresponding model size of GPT-3, like 6 billion or 175 billion model. And then from their based on this relationship, they identify that for a parameter budget of 175 billion models, the optimal depth should be around 80 layers instead of 96 layers that is configured in GPT-3. So basically, they build a counterpart model for GPT-3, which they use around 80 layers. So it's like 76 layers in the transformers. And then they keep the model size relatively close. And then they see a boost of the performance of the test. So which means that actually it will, so this actually will help of identifying what is the right configuration given the model parameters budget or computing budget. So if you are interested, I think you can search Jurassic 1. I guess they will have Jurassic 2. So you can look at the Jurassic 1 and this paper I think is very interesting to read of how they use the scaling laws to configure more effective LLM. Like similar size model, but will have a better performance due to it sets the configuration at the optimal point without trying them one by one. People actually find that the effects of the hyperparameters on big language models can be predicted even before you run the training. Like what is the optimal, like Adam or SGD, right? So you can test them out in a smaller model, model depth, and also architecture choice. All of this actually can be explored with a smaller model, and then once you decide the choices, then you can scale it up to a larger model, and then the performance should still holds there. So basically, this is a procedure, right? So train smaller model first, establish a scaling law, right? That log linear relationship, or you identify like different regions, how the relationship will change, and then you can select your optimal hyperparameters based on the scaling law predictions. let's move on to the joint scaling of the model size and the data size. So basically the question is, do we need more data or need bigger models? And actually, I think we all know that if we have lots of data and we just train smaller model, like small models on this data, basically the lots of data actually is wasted, right? Because the small models cannot fully capture the patterns that exist in this massive data set. So this is what people find. So each line corresponds to the same model size, right? So this is the purple one. So this is like a very small model, and this is the second smallest model, and the yellow one is kind of the biggest model, like among these 6 models. And then the x-axis is the tokens in dataset. So it's basically the data size. And then y is the loss. And you can see that if you use a small model, like the smallest model, even if the data size increase, the performance actually will saturate, will no longer improve, even the data size increase, right? However, if you use a large model, such as the yellow model, as you increase the data size, the loss will improve. The loss will continuously decrease when you increase your data size. So to model this phenomena, like observed, then people actually feed a polynomial to this relationship, right? So I think n is the data size, m is the model, m is the model size. And then they find that you can fit a polynomial to that equation, and people find that it actually surprisingly provide good fits to the model data joint error. And of course, there's like a different model also. Like people also propose like a different empirical formulas to fit these data points. How people going to like kind of test this out, right? So basically they so each dot here is using a fraction of model parameters and a fraction of the model size. So this is the smallest data set with the smallest model. And along this line, you kind of gradually increase your data size till the full data set you have. And along the Y is like you gradually increasing the model size, right? And the green dots are basically you just actually train the model on this data size, and then we report the test loss performance. So this green one are actually observed, and then you are going to fit a linear line to the green line. So the red dots are the kind of the extrapolated dots. So this is the extrapolated dots, like when you actually train, well, you can first actually derive where this red dot is based on this equation. And then you can fit them to this equation, like because of the green dots, you can derive the parameters of alpha and beta, and then given the red configuration, you can calculate what is the estimated errors there. And of course, you can, just to see whether the prediction holds, you can also measure the actual error for this model configuration and data size. And you see that they actually, you predict actually pretty well based on this simple equation. Right, so all of this, so this is the estimated error, this is the measured error. Yeah, so it actually fits this line very well if the prediction is accurate by the equation. If it's the prediction is accurate, then they all should align on this y equals x. People actually identified this phenomena for ImageNet, right? So this object detection problem, and also the same for the wiki text. So another NLP text, they observe the same phenomena over there. So basically, you can trade off your data size and model size with this formula, just to kind of to estimate what is the loss given your current data size and model size. And then there will be always a question is, do we need to connect more data or do we need to increase our model size, right? And people really identify the data size bottleneck as, I think this graph, this figure also shows up on the earlier slides, right? So if you just keep the data size the same, even if you increase the model parameters, the performance will not continuously improve, but you may need to increase your data size. You need to allocate more resources to connect more data so that the performance can improve. And people actually identify another empirical loss to see, okay, given the data size, what is the optimal data model size? And the relationship is this. So basically, this is your number of tokens in your data, and this is your model size should be. So people find that for 22 billion token web text, you can actually optimally fit a 10 to the power of 9 parameters model to train on this 22 billion. If you further like increase the model size, then it actually is wasted. Your computing power is wasted. It would not help much if you further increase the model size, because if you further increase, it means that you need to increase your data size also to fully kind of use the power of the model at that size. I think it's like a very interesting kind of have some empirical reference of should you train a bigger model or should you connect more data for your task. There will be also like compute trade-off, right? So for a fixed compute budget, should you train a bigger model? So basically you can increase your model size, or should you train a smaller model and then run it more steps, right? So you can train it iteratively, run more epochs, run more steps for that. And this is also very interesting plots. So the X is the model size, the parameters model size. Y is the loss. And then this curve is the, say you have a fixed computing budget. So this is the computing resources, like combining the model size, combining the steps you run to train the model. This is your fixed computing operations that you have taken. So when you increase your model size, you will run fewer steps, right? Because you have a fixed compute budget. So if you increase your model size, you run fewer steps, then it means that you may risk undertrained, right? You may not fully train the model because you need to run smaller steps, fewer steps. On this wise, it's like you have smaller model. It means that you will actually train more steps since you have the same computing budget. So you will train more steps. Your model will likely get kind of overfit. But I think in terms of the slope, it actually will kind of stay there for a while. The Tesla will stay there for a while until you really overfit by a lot, and then it will goes up, right? So you can see that as you have more computing power, for example, the yellow, so the yellow is like you have the most computing power, and you see that the test loss, when you increase the model size, your test loss will also improve as you increase your model size, right? And at some point, the yellow curve will also goes up. Like if you really grow the model like to a really huge model, it may mean that you will undertrain that model later, and then the curves will go up given the same compute budget. Same is a plot over here, right? So it means that you have the same model. So this is like you fix your model parameters, you fix your model size, but you have the same computing power. No, so you kind of, the X is your computing power. So you will use more and more computing power when you run more steps to train the model. And then you see that for a fixed model size, the performance will kind of saturate after some point. And for really large models, such as the yellow one, it would require a more computing power, so that the model is fully trained for that data sets. And it's another very interesting to see is that the lower bound kind of still holds the log linear relationship between the loss and the compute. So somehow the log linear relationship still holds for the lower bound over here, right? So this linear line over here between the loss and the compute. This one, yeah, so it's also interesting. Is about should we given the compute power, should you what's the optimal model size should we config, and how should we scale the training? So scale the training means that we can train huge batches, but with smaller, like the same number of steps, right? So if you have more compute power, we can choose to train a huge batch in each step. But we keep the same number of steps. Or we can fix the batch size, but we can train more steps. So which is better? And then people find that actually, so this blue line actually tells the optimal model size given the compute. People said the first priority will be always to increase your model size. So if you have more compute power, and again, depends on the data size, right? You have that optimal model size given the data size. And then if you have more compute power, people find that if the model size is a bottleneck, for the data size, for the given data size, increasing the model size will always gives you the biggest gain. And comparing like huge batches or fixed batches, they also find that huge batch wins over the fixed batch. And you can just choose to run pretty much the same steps in the training for process, but you can train the models on huge batches if you have more computing power. And they say that maybe it's a good news for the data parallel processing, because the larger the batch, it means that the more parallel you can run in your training jobs. So the recap for the scaling laws of models and compute. So actually the log linear relationship still holds for the model size and the compute. Yeah, so we can again use the small models to figure out what is the best configuration, what is the best model size and compute, and then we can extrapolate it to bigger models, and then we can try to make smart resource trade-off, right? So we can use that empirical equations to figure out what is the optimal model size given the data we have right now. Is the data the bottleneck or the model the bottleneck? And then we can do better actions that we should allocate more resources for models, or we should allocate more resources to connect additional data. Looking at the scaling laws and the future. So I think we all have a question regarding, can big language models solve everything? Right? So as we grow larger and larger model, can ChatGPT, can all the other like large language model, can they solve everything? Every task, like NLP tasks, computer vision tasks that we have. Actually, we can use scaling laws to answer this. So for each capability, like question answering, translation, or like SAT testing, coding, right? So for each capability, we can actually build a scaling law for the compute capacity of the data size, model size, etc., and also the compute resources. And then we can extrapolate the scaling curve to predict what the performance will be like, say if we invest more resources in compute, say if we grow the model even larger, can it get us a better performance for this capability or task? So here is some example, right? Like this is a classic AI challenge. So it's you give a pair of sentences. So you have two sentences, and then you give that, so it's too large or it's too small. and then it asks you to predict what is it, right? So what it refers to. So for the first sentence, you can say that it's too large, that it can mean the trophy. Or if it said it's too small, then it means it's the suitcase, right? So yeah, so basically it's just kind of like to predict what it refers to, what she refers to, and what who are they, the zebras or lions. So current GPT performance after like training, like few shot training for 50 examples can get 77% accuracy. Can we push this further? So we can use the scaling laws, right? So this is the x-axis
Yep.
is x-axis. Sorry, any question? X-axis is the model size, and Y is the accuracy. And then you can see the raw beta model, the state-of-the-art model, and also what is a human performance over there. And then this is GPT-3, zero shot, blue line. Green is the one shot, orange is a few shot with 50 examples. And when we reach 157.5 billion parameters, we get here, right? So the few shot with k equals 50, we get the performance over here. So actually, it's going to be a log linear relationship. If the scaling laws holds, we can actually look into the future. Like if we get 64 more parameters, we would potentially get us to the human level of this task. Yeah, but it's a lot, right? It's a lot to scale the model size, and also if you train the model size, you need to connect like correspondingly that big data sets in order to support the training of such a big model. But from the scaling law, at least we know at least we know that we can do an estimate, right? So we actually need 64 times of the GPT-3 size for this task, for it to get to the performance of human level. And also, for example, for the SAT energies test, right? So it's a multi-choice problem, and you want to pick what is the correct answer from the choices you have. The same here, you can do the extrapolation. So it kind of holds the log linear relationship between the model size and accuracy, and then you can extrapolate to see when it will get to the human level performance over there. But there's also some task that the performance actually does not increase when you increase the model size. For example, the word in context data sets. I think it's like whether this means the same meaning. So for example, whether the bad word has the same meaning given different context. So the label is true or false. And GPT-3 finds that it's the task like this pairwise comparison is much harder than just a single context prediction. And thus the performance is kind of like the ratio is very small. It's almost like stays as a line. So yeah, it's really hard. Even the scaling laws holds, it means that yeah, increasing the model size won't help. You need to identify like build better models. Basically, you need to find better solutions for this, and scaling it up won't help in this for this task. Another phenomenon people found is the phase transition. Phase transition is like for example for this like 2-digit addition, 2-digit subtraction to 3 digits, 4 or 5 digits and more. The performance, the accuracy will suddenly increase after some kind of threshold. So that's why they call it like emerging capabilities of LLM. It's not like a linear relationship, but it's like after some threshold, say after 7 billion parameters, the performance suddenly gets so much better. And then you will see that the addition and subtraction performance accuracy will increase by a lot. And it only it's a discontinuous jumps in the performance. And people right now call this emerging capabilities of the LLM. And people do notice that the LLM, the large language model, depending on the difficulty of the task, the threshold may become different, right? So for the more challenging tasks such as coding, like assist people to code, the threshold turn, the transition may happen later. Like it may happen at I don't know what, like 50 billion parameters. Well, for the 3-digit addition, which is simpler task, the turning point will happen earlier at say 5 billion or 6 billion parameters. Yeah, people right now still haven't, like, what is the reasoning behind that? Like, what is causing this phase transition? So this is perhaps the biggest unknown in the language model scaling, and how we can predict this turning point, this phase transition. I think right now is still unknown, like how we can actually predict this sudden jump of the performance. So this concludes the slides, right? So yeah, so some tasks it will just improve continuously while scale in the log linear relationship. And some others may have this phase transition and have this emergent behavior of the LLM, which is hard to predict right now. And also there will be some tasks which is still very challenging, such as like word in context prediction, like a pairwise prediction. Like scaling the model won't help anyway, according to the scale laws. So yeah, so the scaling laws can help with the key question. So what problems can we brute force? We know at least like what problem that we know, like scaling the model up, the performance improve, and what tasks that we know that adding additional model size or computing power right now, it won't help. Instead, we should look for new architecture, new solutions for that specific task, or maybe a new optimization objective, for example, for that task. Yeah. So yeah, I think, I hope that this is a surprising and useful and fun session for you. I think I'm going to try to practice some of the empirical findings to see that how my data and my model data size and my model size match with each other, and also use the small models to identify the best configurations so that I can without hyperparameter tuning on a really huge model to save some cost for the parameter fine-tuning process. Yeah, that's all I want to show. I'm open to any question.
Hi, I was under the impression that math cannot be done with the LLM or ChatGPT, but I see that you have here that you could actually do very simplistic math. Well, can it do or can it not do math? Because
I think it can. I think recently I also read a paper. I think the news is a while back. But if you search, which company does that? They develop a specific LLM just to do math. And I know that the ChatGPT, they also claim that they right now doing a better job at math. They are enhancing their math capabilities.
Because they may be using Wolfram or spawning.
Yeah, maybe it's Wolfram. Yeah, maybe it's Wolfram who is doing that. Or maybe it's like LLM figures out like what functions to call.
But
and then take
LLM itself cannot do math, is what I was told, right? It doesn't have the concept of math.
No, I think it can do math. It's just like it's not guaranteed. For example, for the 2-digit addition, 2-digit subtraction, it can still do pretty well. when it reaches 155 billion parameters, but is it really worth it? I think maybe there should be a more efficient way to do math
Okay,
there.
thank you.
And even it's like even if it can do such a high accuracy, it's not guaranteed 100%. But it's such a simple operation, we all know, right? So we should find and identify other ways to see whether the LLM, we can use the LLM to figure out the logics. And once the logics, the steps are figured out, they can call corresponding tool to do the simple operation, and then the LLM can combine together. Maybe that is a better strategy than just train an LLM to do the simple math.